So this tutorial will cover two-point linkage mapping and composite mapping, like we discussed in lecture. And I'll go through some worked examples. I'll start with a sample problem, and then you can try to do the 5 additional problems on your own. And as needed, you can keep the recording going to find out the answers. So the first one, the practice problem that we're going to look at, is shown here. So this is how they will look. It says consider 2 linked genes, because we only do linkage mapping if the genes are linked, in a specific plant species. The allele for tall plants is going to be represented by the uppercase S, is dominant to the allele for short plants, little s, and the allele for red flowers, big Y, is going to be dominant to the allele for yellow flowers, little y. A test cross is performed, and this is how the mapping test cross is always done, with the heterozygous parent, big S, big Y, and then the completely recessive parent, little s, little y, little y. So you would have to have some reason to think that the genes are linked in the first place, and then you set up this particular cross to figure out how far apart the genes are on the chromosome. That's the map. So the following, you do the cross and you count these progeny. So you have offspring that are tall with red flowers, tall with yellow flowers, short with red flowers, short with yellow flowers. One thing you want to keep in mind is that, turn this on to presentation mode. One thing you want to keep in mind is that the completely recessive parent is going to always provide a little s, little y allele combination to each offspring. And so for that reason, I don't write in these genotypes, I don't write the contribution of the recessive parent. So the tall red individuals are big S, big Y, little y. The tall yellow are big S, little y, and so on. But I eliminate that little s and that little y because it will be the same for each of these offspring groups. So really what I'm showing you in the shorthand is what allele combination is coming from this double heterozygous parent. And that's all we really need to focus on, because the number of crossovers there is going to give us a measure of the genetic distance between the genes. That's how we do genetic mapping. And so you count up the number of offspring, and the first thing you have to do is add these up. So 283, I have my calculator here, 813, 826, and 321. So 2243, let me find a pen. So 2243 is my total here. All right. And so you're going to then identify which of the groups represent what we call a parental combination of alleles and which are recombinant. There's a simple rule. The parental allele combination is going to be the biggest numbers. So these are the parental allele combinations. So these are parental, these are parental. And then the recombinants are the other two groups. So the 321, that number of offspring, and the 283, those offspring have chromosomes that resulted from a recombination originally in this, in meiosis, in the double heterozygous parent. And so you add those together. So I'm on step 2, calculate the recombination frequency by adding together the number of the recombinant group offspring divided by the total. And so 283, 283, and 2243. All right, I got 26. You do convert it to percent. Point, let's say 93. Don't round off too much. That's the percent recombination frequency but based on our rules of genetic mapping, we say that's the number of map units, 26.93 map units. So if you were to make a map, you would put the genes here, and you can put either big or little, just S and Y, because it depends on which organism and which chromosome, which allele are there, but the gene S and the gene Y are spaced apart 26.93 map units. So that's the map. You can do like a brackets or arrows or something like that. All right. Actually, I probably should have done not arrows there, but rather just a straight line representing the chromosome. And then the brackets can be right here. So from S to Y is 26.93 map units. Okay, so you add together all the offspring that you counted in your cross. Then you add together the two smallest number groups, because those are the recombinant groups. They got a crossover chromosome from the heterozygous parent. And then you divide by, you add those together and divide by the total, convert to percent, then directly convert to map units that way. Okay, so problem 1, we have Harry is going to be the big B, and bald is little b. Brown is big E. Blue is little e. And in some ways that doesn't even matter, because when you look at the offspring, it doesn't really matter what the allele combinations are. It matters whether they're the most common. So these are the most common. So these are parental allele combinations. And these numbers here are smaller. So those are recombinants. So you're going to add together the recombinants, and this is going to yield your recombinant frequency. I forgot to add together my total, so let's do that. 868 plus 900 plus 115. Oh, that one came up nice and round, 2,000. I made these problems up, so sometimes I make the numbers nice and even, sometimes I don't. In real data, it usually is not going to come out even. Okay, but 117 plus 115 divided by 2,000 is 11.6% recombination frequency. So the distance between any allele of gene B and any allele of gene E is going to be 11.6 map units. Okay. So on the next one, if you want to freeze the video and solve it yourself and then watch me work it out real quick and see if you get the same answer, I think that's a good way to go. So this is it. In strawberries, juicy is dominant to dry, giant is dominant to tiny. Double heterozygous juicy giant females are pollinated by dry, tiny males, and the following offspring are counted. So juicy, giant, in this case, it doesn't, the order in which these are presented doesn't matter. The biggest number is always the parental, and the smaller numbers are always the recombinant. Let's add up the total. 453 plus 54 plus 67 plus 426. This one comes out to be a nice round 1,000. So we're going to add together the smaller numbers, 54 plus 67 divided by 1,000. 12.1. That's percent recombination frequency, but also map units. okay? And just a note, I actually calculated 0.121 here, but I can do it in my head. I convert to percent, 12.1%, 12.1 map units. If you need to write out all the steps, that's fine too. Okay, now on problem 3, this is a composite mapping. Let's say that you have already calculated a series of 2-point mapping distances using the method we were just doing in the previous examples. And then you're going to composite all of these pieces of data together into a single map, or maybe more than one map. So a linkage group would be a group of genes that are linked together, and each segment in the linkage has to be less than 50, because 50, remember, a 50% recombination frequency is actually the number you would get if the genes are not linked. So you can't rely on a 50% recombination frequency. So that would be the first thing I would do, is go through this data, and anything that's a 50 is not going to be informative. So that you can't rely on a 50. Those genes could be linked, but they're not going to be. I wonder why that's a 3. Interesting. D, C, E. I think that should be C, E. C to E. Okay. So A to B is linked at 10 map units. You have all these little pieces. A to B is linked at 10. A to D is 14. I usually actually start with the biggest piece, and this is not to scale, but A to D is 14. A to B is 10, and B to D is 4. Does that all make sense? Do the pieces all fit together to make one map whose individual pieces match with the 2-point data? Yes. So that's your map, A to B, B to D. You can rotate this around. So if you, for some reason, wanted to, you could put D on the far left and A on the far right, and then just place B. And again, this is not to scale, but put the 4 here and the 10 here, then that's the same exact map. So rotating the map doesn't matter as long as you keep the relative distances in the right place. But all the genes that show a 50 recombination frequency, that's not useful information. All right, now on problem 4, I'm going to go through, we're going to do the 2-point mapping on all 3 of these. So we get the distance from H to WG, and that's 2 genes. We're going to get the distance from WG to LG, and we're going to get the distance from H to LG, and then we're going to composite all 3 together. So on this one, let's total this up. My video is going to run out of time. It looks like I'm going to time out, so I'll start up a new video and pick up right here. Just keep watching the playlist.